In these sections, we're going to look at very interesting but very special applications of the Mohr circle to study the transformation of the stress in 3 dimensions. But here I want to emphasize this is a very specific and very particular example with certain restriction, okay, and with a certain restriction, and I will mention this one. So usually the Mohr circles are is a build-up for taking care of the transformation of the 2-dimensional stress, and in 2 dimensions, the transformation in 2 dimensions. But here we can generalize this kind of concept to 3-dimensional stress, as long as certain situations or certain conditions are satisfied. In other words, if certain particular conditions are not satisfied, and then the Mohr circle technique wouldn't be able to apply to solve the transformation of the stress in 3D. Okay, so keep these particular conditions in mind, and I'm going to talk about this one quickly. So here the transformation of the stress for an element rotated around the principal axis can be represented by the Mohr circle. So here the keyword is this: the Mohr circle stress element rotated about or around the principal axis. So this is the keyword. So that means what I mentioned, the particular condition is such that for you to apply the Mohr circle for taking care of the 3-dimensional transformation of the stress, you must start with the principal direction. This is the very strict condition to meet before you can do so in this section. If not, then you can't. Okay. So now we start from the principal directions. Then here let me explain. So from using these examples, let me try to see how much I can do. Seems not. So this graphic is pretty generic, and let me move on to my next slides and give you more explanations. And basically these slides you only need to pick up is this: if allow us to do the Mohr circle for 3-dimensional transformations, then you have to start with the principal orientations of that stress element. So keep this in mind. Okay, so we see how can we do this one. And so here we look at the how can we generalize from our 2-dimensional the plane stress and into the 3D view. Okay, so for example here, if you kind of simply extend the stress element in the dimension in the 3rd dimension, then basically come to here. Okay, so again, if you are the little guy and this is the axis, if you're sitting in this axis onto this axis and looking into the block in front of you, you will see is this one. Okay, if you are a little guy sitting in that orange the direction, so projecting to you, what you see is this one. So that is the at the beginning of this chapter I said this is a simple and easy graphical representations of more general 2-dimensional case represented in 3D. Okay, but now we want to extend from there one step back and using the 3-dimensional to explain how the Mohr circle can be applied for 3D. So now we start with this one. If we start with the principal, again we start with the principal direction, something like this one. Okay, then our step is this: you're simply working as the little guy. Okay, so for example, you are the small guy, say sitting in this axis and looking into here, then what in front of you, you will see, let me do this one here. So if you're looking from here in front of you, exposing a sigma A, projecting to you a sigma A, B, something like this one. Okay, so this is sigma B, sigma A. So now you keep moving yourself to the other two axes. For example, here to this axis, you're sitting here and looking into that directions. So in front of you, you can see is this is sigma C and this is the sigma B. Okay, so projecting to you, this you will see is this one here. Okay, so the symmetric. Then the final axis to which you're going to sit on would be, for example, you sit here. Okay, so you are sitting on this axis and kind of looking downward. So you will see in front of you would be something like, let me see, projecting to you is this surface. So from here is a sigma A, and then on this one is the sigma C. Okay, so that is this case. So for illustrations, why not let me make up some numbers here. So for example, say let me say sigma A equal to 100 and sigma B equal to 10 and sigma C equal to 50. Okay, so here sigma A equal to 100, sigma B equal to 10. So now based upon this one, we can individually draw the Mohr circle. So let me put onto the coordinates. And this is the normal stress and this is string stress. Okay, that's a coordinate. First one will build it up. So now we can begin to draw the Mohr circle. So the first one, let me draw the Mohr circle for this case. For Mohr circle for this case, basically you can repeat the calculation. So 10 plus 100 divided by 2 is 55. And then the radius for this case will be 45. Okay, and I do the quick calculation. So basically here the average is 55. So let me put here, the average 55 here. So basically here, okay, so basically here is 100 and this is the 10. Okay, and this is the center is at 55 here. Okay, so okay, let me just put it here. Okay, and keep in mind this radius equal to, say, let me call this is R1 and 45 here. Okay, so now let me draw the second Mohr circle, saying using the same color here. So now I'm going to draw this circle here. So sigma C equal to 50 and B equal to 10. Okay, so for this case, the average equal to 10 plus 50 divided by 2 equal to 30. The average, let me call the radius R2 equal to 20 here. Okay, so again, R2 based upon our previous calculations. So basically there okay, something like this one. So this is 50 and this is 10 and the center is here. Okay, now I continue to draw the third one here. So draw the third one, this is the 100 and this is 50. So that one should be, if you draw it correctly, that should be here. The three Mohr circles, and here I use color to indicate which viewpoint, and here I use a color to indicate which orientation we're looking into. So basically each circle showing here is a projections of the information to your viewpoint of the three-dimensional stress elements here. And the three circles, once you draw them completely correctly, the three circles must be tangent to one from another. Okay, something like this one. So now we simply again we sequentially change our view of the stress element in the way to get the projected information, and from there we apply the two-dimensional Mohr circle, and for this case. So from here we have the applications, and for example here for this case the maximum shear stress. So the maximum shear stress, you look at the maximum radius out of the three circles, and from here you can identify this will be the maximum shear stress for this three-dimensional stress element that can experience. Okay, and such a maximum shear stress will occur in such an orientation, in such the transformation that look at from this viewpoint. So if you look at this element projecting in front of you, then the maximum shear stress will occur by rotating. Let me move out this one not to mess up the drawing. So that will be kind of the rotating in this sense. Okay, so in terms of three-dimensional, then basically that could be something like this one here. Okay, so something like this one. Okay, so that is the applications of this kind of Mohr circles. And here I use another example, and here the 10, 2, and 5 individually, just like I did here. From x-axis, if you have this little guy sitting here in front of you, you can see is this one. And from y-axis, if you are little guy sitting here looking downward, you can see is this one. Then you are little guy sitting here and looking that one, you can see is this one. So simply this is the repetition of the similar example in the previous slides there. Okay, so for example here, this is I use a number 3 corresponding is this viewpoint. So corresponding is this viewpoint here. So the maximum occurred is rotating this block, and corresponding to you simply rotate this block in the way, for example, yeah, by rotating that way. Okay, and another example here, for this case, we are given the 2D, the plane stress. The plane stress is in this way. So this is not in its principal directions. So you cannot directly apply the techniques we talked about from the beginning of this section so far. So you have to do is you need to first rotate it into its principal direction, something like this one. Okay, so you need to rotate it, and how to rotate it, simply apply the previous sections, and given this one you should be able to find the principal directions and say theta p1. Okay, determine the theta p1, and then from there this is the maximum and this is the minimum. Okay, so basically repeat the previous section. So starting from here, they may translate that information to here. So basically the 3D view is like this, and then starting from here, then you gradually change your viewpoint from x direction, from y direction, from z direction. You have the three things. Then from the three things, you simply build out the three circles. Okay, and from there again, the maximum shear stress is happen on the red dashed one. So that's a maximum, sorry, tau maximum. Okay, the tau maximum, the red one is 8. So red one is corresponding to is this one. So let me call this is number 2. This is the number 2 view, and then this first circle one is a number 1. Okay, and oh sorry, this is number 1. Number 1 is here, and the blue one, this is number 3. Okay, so that individual viewpoint. So from here we can quickly see the kind of grab all the informations. So again, this is another similar examples here, and then for example here we want to determine finding the maximum shear stress. Okay, so again this has been in its principal directions. So basically we simply do it, and so rotating about the axis. So here let us do this one. So if we do the looking at this viewpoint, and here in front of you, and let me do this one carefully in front of you. For this case, what you see is this one is sigma y equal to 2, and then this is sigma z equal to 5. Okay, So this is 5 and this is 2. So for this circle, then basically let me use the color here. Okay, then let me use the different color. So from y-axis, so looking at from this viewpoint, so in front of you, you see we're projecting is this surface. So this is the sigma x equal to 10, and then this is sigma z equal to 5. Okay, so 10 and 5, so that is a circle corresponding to this one. Then finally we have the change in our view, so that will be let me do this one here. So we right now we see is this surface, and then projecting to us is 10 sigma x and sigma y equal to 2. So for that case, that corresponding is this circle. In this circle, the maximum, the absolute maximum stress occurred. Okay, maximum strain stress occurred. So maximum strain stress occurs in the blue sense of the orientations here. So right now in front of you, this is 10 here. So for example here, let me assign our coordinate here. Okay, and here let me assign in front of you, this is the say x and y coordinate. Okay, so here this is our x point, so this is the plane, x plane, and 10 0, and this is the y plane, and that is 2 0 y. Okay, so that is our y. So now the maximum stress occurred on the blue circle. So the blue circle, let me say the north pole and south pole we're connecting. Okay, so now if you choose this sense, so x will move to x prime. This is our 2 theta s. Okay, and say 1. So basically from here you can see theta s 1, 2 theta s equal to 90 degrees. So this is 45 degrees. Okay, and then the rotation is in this sense here. Okay, so that means when you do the rotation, you rotate this blue one by such sense 45 degrees. Okay, and then in this sense, so that means you simply rotate this element. I'm going to mess up the drawing by 45 degrees, and in terms of the three-dimensional, really is messy. So let me get rid of unnecessary information. So right now we know we're going to rotate from this view by 45 degrees. So in 45 degree orientation, in that orientation, the maximum strain stress occurred. So rotating the three-dimensional block in 45 degrees, this is the orientation in which the 45 degrees align to the 45 degrees. So in this plane, the maximum strain stress will occur. Okay, so 45 degree can be in this, or the other options could be this. So let me link to this. Okay, so something like drawing here. Okay, so basically the maximum strain stress will occur in, I would say, the crystalline surface or crystalline plane of the, say, if we would treat it as a crystal, then this will be the crystal internal plane in which the maximum strain stress will be produced under this kind of the loading conditions here. Okay, so this is a very quick example, and then here simply ask you to exercise repeating our previous example for different value, for 3 different possible value of sigma z, 0, 45, and minus 45, and you simply repeat the building the 3 circles again from their principal directions. So for this case, again, here you can clearly see this is not in the principal direction. So by all means, the first step, you need to build up from their principal directions. Okay, so that is sigma A, sigma B. Okay, so once you conduct in the principal directions, then the element will be something like this. Okay, so one normal stress is 145 and MPa, and the other side is symmetric, the same. and then sigma b equal to 25, okay, and then the sigma z is here, okay, so the 25 and 145. So this is the starting point, your starting point of drawing the three circles. Then you simply keep changing the sigma z for the three different values, repeating the steps. Okay, so that is the answer for your reference. And again, this is another example. One more time, the given one here is not in his principal directions, and do the transformation there. So with this one in mind, then basically the case would be something like this. In the principal directions, in the principal directions, the distribution of the stress will be 120, and one is 30, okay, and then the sigma y. Okay, so something like this one. So in the principal direction, then you start from here, then you try to solve this problem, and just something like this one here. Okay, so here we I try to get used the last two slides to explain a little bit more why we are concerned about using the Mohr circle, and what the advantage can provide to us, and in particular here why we most of the time we concerned about the principal stresses or the maximum distribution stresses, why we want to do that one. So for example, we start from the given the loading case like this one. So this is our chapter 2, the axial loading, and we simply pick up an orthogonal orientation aligned to the xy like this. So we have the loading conditions like this one, then we can apply the Mohr circle. Xy corresponding is our stress element here. So here we can apply the Mohr circle to know, okay, the CD, this one corresponding is our maximum strain stress. So the maximum strain stress occurred in this case is 90 degrees. So that means in this case happen is 45 degree orientation. So this is x prime, y prime, okay, in that sense. So this is x prime, y prime, like we're showing here, x prime, y prime, okay. So in this orientation, we have a such distribution of the maximum strain stress. So if any stress components exceed we call the yielding stress, the maximums here, and for certain material, and the maximum, the yielding stress, okay, sigma y, this is the particular material properties embarks the plasticity. Okay, the plasticity is a permanent deformation of a material which is overloaded beyond its elastic regime. Any material under elastic deformation will be able to recover back to its original shape as long as the loading are in elastic regime. If the loading is so big such that it's beyond elastic regime, that means beyond the yielding stress, then the material will be deformed permanently. And very likely, and once the material being in the plastic domain, then long-term fatigue will cause the material failure. Okay, so that we use this one as kind of threshold. We wish our application, the maximum, whatever the maximum strain stress or maximum normal stress is lower than this one, okay. And so that is the application for this one. Another similar example here we consider in our chapter 3, the pure torsions there. So here we have a torsion, and we know we can determine the maximum strain stress on the surface. Maximum strain stress on the surface is equal to this formula. So that is our chapter 3 formula there. So again, under these situations, then this is y coordinate corresponding the point is here. So in this case, if we rotate to try to find the principal direction, principal stresses, so this is 90 degrees. So such that this is 45 degrees in that new transformed orientation x prime, y prime. For example, x move to x prime here, and basically the normal stress how much is tau maximum? Okay, x prime has a coordinate maximum 0 because this radius is the radius equal to maximum. Okay, and so y move to here, y prime has the coordinate minus max and 0. So that means here is the maximum. Okay, so in this transformed x prime, y prime, we have the normal stress being determined, that is in magnitude maximum, in magnitude equal to maximum. Okay, so again, we can also determine whether this material will be exceed the yielding stress, and to study furthermore about the reliability or lifetime of the material. So this, with this basic information, and very likely for students from mechanical engineering, and those tools will help you in the future for machine design. And in that case, the plasticity considerations or fatigue, some kind of the lifetime prediction, that will based upon this tool here. And for students from civil engineering, and you will have the similar, the topics will be covered in your design of the column, the beams, and structural material for this kind of case. Okay.